Hello?
Hi, Kudus.
Okay, good morning, ma'am. I just wanted to be sure I can be in. Yes, ma'am.
Yeah, I'll be sending the artifacts out. Don't worry, I'll be sending it to Odds Research Hub so that you don't send it like
Okay,
the link, the YouTube link.
okay. I already shared already, some.
But not to the Hub Research Hub. I'm just sharing so that you don't share it.
Okay, ma'am.
Mm. Good morning, Professor T.
Good morning, ma'am.
Well, I'm really grateful. Thank you.
Thank you, ma'am. Yes, ma'am.
Good morning. Welcome everyone to today's session. It's the fourth in the series of lectures on quantitative data analysis, and I'm sure we've had a swell time listening and learning from Dr. Taiwo. Dr. Taiwo will continue the conversation this morning over the next 2 hours. I encourage us to listen attentively to him and put our questions on the chat box during the course of the lecture. Thank you. So you have the floor, sir.
Thank you, Dr. Lawal.
And just before Professor Taiwo starts to speak, please let's give ourselves an extra 20 minutes today because he has to finish last week's session and we're also rounding up. So we might extend this 2 hours by 20 minutes. Apologies for that. Thank you. Over to you, Professor Taiwo.
Thank you so much, ma'am. Thank you, everyone. Good morning and welcome. Like Prof said, we'll be tidying up today, and the topic for today is regressions and contingency table analysis. I will just set the ball rolling right away. The disclaimer is still intact and still in force. This presentation contains some materials I adapted or referenced from various internet sources, and these materials are solely included for educational purposes. I don't claim ownership or original authorship of this content sourced from external references, and full credit is due to the respective authors and creators of these works. I will want to just still remind us of the research process. It's just conveniently the best place to start our talk anytime we are together. That we'll start with a research question, a research title, or research topic. You have your literature review, you are able to find out that the research is valid, it's something doable. You go on with the research hypothesis, and then you have your research approach. By the way, a research hypothesis only works with a quantitative research approach, and there are 3 approaches: the quantitative, the qualitative, and the mixed method. For the quantitative, you are able to do your sample size calculation. You know the number of people you need for your study to be valid. And then you choose the appropriate sampling method for your sample size and variables and measurement scale based on what you have found out from the literature review, the variables you need to collect for you to have your data. And then we spoke about, data collection is just like collecting your variables using whatever means you want to use, either maybe questionnaire, Google Forms, SurveyMonkey, and whatever. And then the next stage after data collection is the data analysis, which is where we have been in the last 4 weeks, today being the last week, and then report presentations, and you continue. I need to also remind us of what variables are. It's just cardinal. You will have noticed that all through our discussions in the last week, we always make reference to variables, the types of variables, the measurement scales. A variable is a characteristic that may assume more than one set of values for which you assign a numerical measure. And a variable, like I said, is a characteristic that changes, and that is different from a constant that does not change but remains the same. We kept emphasizing that we have 2 types of variable. We have the quantitative, and then we have the qualitative. For the quantitative, it can be continuous or discrete. For the qualitative, it can be ordinal or nominal. For today's class, I just want to remind us of what we said about binary variables, because we are coming across it in today's presentation. That's a qualitative nominal variable that has only 2 levels of expression: yes and no, true or false, dead or alive, binary. Don't forget that, please. And then we said another name for binary is dichotomous. When a variable is dichotomous, we say a variable is binary. Then measurement scale are the scales that we use to quantify or to give numbers to variables. And there are 4 types: the nominal scale, ordinal scale, interval scale, and ratio scale. And we said that these first 2, nominal and ordinal, are for the qualitative variables. You can even see that they follow the types of qualitative variable. The interval and ratio scale are for the quantitative measurable variables. And for the quantitative variable, this is the one that is commonly used, for our measurement scale. The hierarchy of the measurement scales: the nominal is the least, is the weakest, followed by the ordinal, the interval, and the strongest measurement scale is ratio, is subjected to all manners of mathematical calculation. We said that once you measure a variable, it becomes a datum. Datum is singular, and collection of datum is data. And data obviously is sourced from variables. So the types of data also follow the classification of variables. We have the quantitative data, qualitative data, and under the quantitative, we also have the continuous data, discrete data, and under the qualitative, we have nominal data and ordinal data. And this has just been like the summary of what we've been talking about, descriptive statistics. This was our first class, descriptive statistics. And then like 2 weeks ago, we started talking on inferential statistics. And I told us that once you have a population from where you make your sample, you have a sample that is from population, you do a sampling, and then you end up with a sample. When you describe your sample, that is what we call descriptive statistics. And if you are now analyzing data from your sample to make inferences, to tell us what is happening in the population, that is what we call inferential statistics. And we've started talking about this in the last 2 weeks, things like correlation, like t-test, like ANOVA, like chi-square, you know, we've been looking at all manners of inferential statistics. So we are still on inferential statistics. And inferential statistics, you know, allows researchers to make decisions on inferences by interpreting data patterns, you know, from samples. Let me just add that. You have data patterns from samples, okay? And it can be categorized into estimation or hypothesis testing. We have under hypothesis testing the parametric test and the non-parametric test. And this is just based on an assumption that the population from where you sourced the samples from either follows a normal distribution or they don't follow a normal distribution. The ones that follow a normal distributions are the parametric test. The ones that don't follow a normal distribution test are the non-parametric test. Okay, so for the analysis, data analysis, univariate is basically descriptive statistics. These two are the inferential, and we have them as in bivariate, univariate, or multivariate. That is talking about the number of variables you are considering in your analysis. Normally, descriptive statistics, you are looking at just one variable. You are describing the spread, or you are trying to summarize it, as it were. Bivariate is when you now have question looking at relationship between A and B, correlation between A and B, the impact of A on B, the effect of A on B, you know, the odds of A on B, all manners. That's where you now have hypothesis. Likewise with the multivariate variables. So for our bivariates, we have looked at chi-square, we have looked at the format of Fisher's exact, we have looked at scatter plot, we have looked at Spearman's correlation, we have done Pearson's correlation also. And as at last week, we started talking about t-test, paired sample t-test. We even looked at a case of ANOVA, that is for bivariate. And we said that this particular one, Kruskal-Wallis, Wilcoxon rack, Wilcoxon site, they are just a non-parametric variant of the parametric test that we saw last week. So in short, what we had last week was our class on t-test, and we said there are 3 types of t-test. Number one is the one sample t-test, where you have just one population, and you are trying to assess the population to a standard, to a constant, to a value, to something that is measurable, either above or below a particular value. It's like if you are checking if there's a difference between, you know, your particular group and that which is the standard or the population value. That's the one sample t-test. And we did a class example. We also looked at it in the SPSS. And we now have the independent sample t-test, where you have 2 separate groups, 2 different groups. Independent sample t-test. You are trying to check if there's a difference between the means of any particular variable you are checking. And we spoke about the 3rd type, the paired sample t-test, which is more like the same set of people before and after, or a different timeline. You know, you are checking a particular variable, you know, at maybe now, and then maybe in 2 months or 3 months time, you are checking the same variable, and you are trying to see if there's any particular difference, maybe based on an intervention or whatever. So those are the 3 types of t-tests that we have, you know, and we saw that they all have different ways of analysis and different ways to read their statistical output. And then the other one in situations where, let me just go back. And I said that t-test cannot go beyond 2 groups. So it's a maximum of 2 groups. And when you are checking, you know, maybe the mean values or mean variation among more than 2 groups, then t-test is not applicable. In that situation, you have to do what we call an ANOVA. ANOVA is the short form for analysis of variance. And the formula for that is the mean squared between over mean squared within. So it's just a kind of statistic, like similar to the t-test, similar to the chi-square. It has a table where we can check values. So it's the ratio of the difference group between group variation or between group difference divided by within group variation or within group difference. And the between group variation is the mean squared between, within group variation is the mean squared within. We said last week that this is the same thing as the sum of squared between divided by the degree of freedom between. While this is the same thing as the sum of squared within divided by the degree of freedom within. There's a table here that just summarizes what I'm talking about. So in summary, our F statistic is variance between treatments divided by variance within treatments. And we were able to look at the logic behind that ANOVA analysis. And the variance is this mean squared between, which is the sum of squared between or divided by the different degree of freedom between. That is for the MSB, and likewise for the other one. And the sum of squared total is just the addition of the two sum of squared, while the degree of freedom total is also the addition of the 2 degrees of freedom. And this is like a sample ANOVA table. Whenever you have an analysis from whatever software, it is presented like this. You have the source of variation, either between samples or within samples. You have the values for the sum of squares, you have the values for the degree of freedom, the mean square for both of them, and the F ratio. And in our tables, you now have the particular one for your p-value, to show if it is either significant or not significant. For our degree of freedom, our K here is the number of groups that you are working with or population. Our N is the total number of the sample size, and our K and N. So our degree of freedom between is the number of groups minus 1. The degree of freedom within is the total number minus the number of groups, while the total number of the degree of freedom is just N minus 1. We did that last week. And like I did promise, I want us to just quickly go through a sample SPSS analysis of t-tests, the 3 types of t-tests, maybe just one ANOVA before we commence with our regression this morning. So I have a sample SPSS table. It has age. Age is a continuous variable. I have gender, that is male or female sex. I have the BMI, basic metabolic index. And for the SPSS data, I have one that is like, say, maybe before, and then I have another measurement. But all these are just crafted. I just populated the cells, just for example, for classwork's sake. So I have 2 BMI, one before, one after. I have lipid level, which is continuous. I have presence or absence of stroke, presence or absence of hypertension. Now, hypertension in this situation is nominal. I'm not putting the figures, so it is nominal. I have the presence or absence, educational level, ordinal, income per day in Naira, continuous. That one too is just. So I will just quickly stop sharing here. Okay, no, before I stop sharing, let me look at the questions we are going to be looking at, for example. So for the one sample t-test, like I said, it's continuous. We are working with just one population. And I have a lipid test, the value for the lipid test for maybe 200 people. No, I think it's 180 people, I will confirm. So I'm trying to look at the effect of maybe a diet to see that if after 3 days, the lipid level has improved. And for my standard or my constant, I'll be working with 200. Remember, it's just a classwork. I'm not working with the exact lipid profiles for human beings, just something like a sample. We can choose any number as our cutoff. And then I'll be looking at the peer test to check the BMI before and to compare with the BMI, after. So 1 and 2, and we'll look at how that is done. And then the independent sample t-test, I'll be checking the BMI among males, comparing it with the BMIs among females to see if there's any statistically significant difference. And remember, for this particular test, we spoke about the Levin's test of homogeneity of variances, or Levin's test of equality of variances, where we have our F statistics. So we'll be looking at all that. And for the ANOVA, I will just be working with the educational level since we have 4 of them. No, is it for 0, 1, 2, 3? Yeah, we have 4 levels. That's obviously beyond 2. So we'll be working with educational levels, and I will be checking them against the BMI. So like I said, I will just quickly stop sharing now and then share, what's it called? Share my SPSS data for us to see, and then we'll try and work with those analysis briefly. So here we have please, can we see the SPSS spreadsheets so that before I continue?
Yes, we can, sir.
Okay, beautiful. So as you can see here, I have my, what's it called? I'm trying to scroll up. Yeah, so you can see here the different data. Age, I have here age, I have gender, I have the BMI, the lipid profile, stroke here is present or absent, hypertension present or absent, educational level, there are 4 of them, income, and this is the second BMI, assuming that maybe I took a BMI before a particular intervention and a BMI after another intervention. So let's just go to analyze, and we are going to t-test. And in t-test, we normally compare means. And as you can see, by putting my cursor on that, it has brought me the different types of t-tests that we have. We have the one sample t-test, we have the independent sample t-test, we have the paired sample t-test, and then we have the ANOVA in situations where it's more than 2 groups. So I will go with one sample t-test. My test variable, like I said earlier on, is the lipid level. I will pick that, I will put it in my test variable. And for my test value, I said I will be working with 200, as the constant. So I put 200 here. Let me check for the options. It's already at 95% confidence interval. I just continue. And then I click OK. And then I'll have to stop sharing to show us the, what's it called? To show us the output so that we can continue our analysis from the output. Beautiful. So as you can see here, that's our output for the one sample t-test. The number of participants is 180, the mean is there, the standard deviation is here. By now we understand how the standard error of the mean was gotten. That is the mean difference divided by the square root of s over n square roots. I don't know, I can't write on this particular place, I would have written out that formula, but we had the formula in our class note. Anyway, this is the result of our test. We have the lipid level, this is our t-value, degree of freedom 179, that is 180 minus 1, because our n is 180. And we can see here our p-value is very significant, 0.000. The mean difference, we can recall how we got that. We have 28.278 here. And how did we get that? It's just the mean of our sample minus the test value here. So 228.28 minus 200 gives us this. And then we have our confidence interval, which we said, we have to consider the values. They are both positive, which shows that it's significant, and it agrees with our p-value here. So that is for the one sample t-test, and that's how it is done. I will go to the paired sample t-test now. I will go to analyze again. I go to compare means, and then paired sample t-test. And here now, I will be looking at the BMI before and BMI after. And you can see here there's a chart that just opened up. And for my first pair, I will go to BMI, baseline BMI, I put it there. And for my second variable, it has to be the same variable I'm measuring after. So I look at second BMI, which I have here, and I put here. Now, this is just one pair. In case I want to do many t-tests, in the same population, and I have different variables I want to check, I can just continue populating it, pair 1, pair 2, pair 3, pair 4, and it continues like that. But for this classwork, we are just doing one pair. The option is still at 95% confidence interval. I continue, and then I click OK. And as you can see here, we have the summary here, the baseline and the second BMI, the total number, the standard deviation, and the error. And then here, the second output here, we have the correlation, and I can see here, it's minus 0.04. That is negative and is weak based on our findings or our studies on correlation. So that's what that means. And at the final one, we have the paired sample test. We have the mean difference here. How did we get the mean difference? This is minus 2.30. How did we get that? It is 25.15 minus 27.46. That's how we got the mean difference. Please don't forget that. And we have the standard deviation calculated from the software, the standard error of the mean from the software. And you can see our confidence interval minus to show that it's significant. And that is also like supported by the key value that we have here. So that is that. So whatever our null hypothesis and alternative hypothesis, by virtue of this significance now, we will just reject the null hypothesis and go with the alternative hypothesis. So let me now go to the third one, analyze what's it called, compare means. And this time around, I'm going to the independent sample t-test. And what is my test variable? I said I was going to check between the BMI of males and the BMI of females. So my dependent variable or test variable is still the BMI. It's a continuous variable. I put it in my test variable. And then my grouping variable here, you can even see the word grouping variable to show that it's categorical. My grouping variable is gender, sex. My grouping variable is sex here, and then I bring it here. However, it's telling me to define the groups here, you know, and what is the definition? I'm going to be working with the measurement scale I used for entering my data. So I will say that in my measurement scale, my male is 1, so I just put 1 here. My female is 2, I put 2 here, and I continue. That was the measurement scale I used, okay? And I click OK. And if you look at it now, you can see here that for male, there were 77 participants. For female and women, there are 103, all of them making 180. So that's for that. Now, we said concerning independent sample t-test that whenever you come to the output, the first thing you do is to look at the area for the Levene's test of homogeneity of variances, which is where I am now. Then you look for the p-value. If you look at the p-value here, it is 0.022, less than 0.05, which shows that it is significant. And if it is significant, that means we reject the null hypothesis of equal variances assumed, and then we go with the output for the equal variances not assumed. So this particular row is the output I will be reporting or working with. And as you can see here, my p-value for this particular output is not significant, and it's also corroborated here by the confidence interval. There's a negative here and there's a positive here. So I will be reporting this particular line of my independent sample t-test, and that is for that. And lastly, let's look at the compare means again and go to our ANOVA, where I said I'll be checking the BMI with the different educational level, and as it is, it's already there, okay? I think that was when I was trying to work on it last week. So let me just go back and let me just show us how we came about that. So you can see here the dependent list. You must know what is your dependent variable. And my dependent variable is the baseline BMI, basic metabolic rate. So I pick my dependent variable to, what's it called? To my dependent list here. By the way, you can have many ANOVAs done. So I can pick as many dependent variable. Maybe let me just give it another, let me pick education also and put here. So I have 2 dependent variables, but I'm checking the 2 of them with my educational level because that's the only variable I have in my sample SPSS list that is more than 2 groups. Educational level, I have 4, and then I put it there, that's the factor. I go to contrast, okay, I don't need anything here. I will not pick any post hoc here for now because I told us the post hoc is necessary if by your ANOVA test you find out that it is a significant test when your p-value is less than 0.05. So let me just click OK. And then there are going to be 2 results here. The first one is for the baseline BMI, you know, and you can see the between groups that we spoke about and within groups. And you can see the sum of squared between, sum of squared within, and the total sum of squared. Degree of freedom between, degree of freedom within, mean squared between, mean squared within, and the F statistics and our p-value 0.07. This one is greater than 0.05, so it is not significant. Likewise for the income between within, and the total, we have all the values of the sum of square, the degree of freedom, the mean square, and our F statistic. It's also greater than 0.05. So both of them are not significant. I don't need to do any post hoc because they are not significant. So that is just an ANOVA. And if you look at this ANOVA, it just follows that table I showed us of the summary of an ANOVA analysis. So I stop sharing here, and then I go back to our class, what's it called? I'll go back to our class note for today, and we continue from where we were. Awesome. So that's for the analysis of variance. 1 minute. I want to. Okay, so for today, we are going to be looking at regressions, understanding and interpreting regressions, and then we'll also look at contingency table analysis. Now, back to that chart talking about inferential statistics for the bivariate, we have here simple linear regression, and it's coming under one continuous variable of dependence and another continuous variable of the independent variable. And for the multivariate analysis, we also have the multiple regression. We are going to be talking about this. We will talk about logistic regression. We will talk about multinomial regression. We'll also talk about ordinal logistic regression. So there are 5 types of regression that we are going to be looking at very briefly today. We continue. But before we go on, I remember at the first class during descriptive statistics, somebody asked a question about multivariate and multivariable analysis. And I said the person should hold on, that it's part of what we're going to be talking about in the course of the class. And I want to quickly mention the difference here. So multivariate and multivariable are different statistical terms that describe different types of analysis. So when we say multivariate, and by the way, the context with which it is used also matter. When we say multivariate analysis, it's used to describe statistical models with multiple dependent or outcome variables and multiple independent variables. So we have like X1, X2, causing maybe reaction on Y1, Y2, Y3, something like that. So these are multiple outcome variables. And then we have multiple independent variables. And it doesn't have to be multiple. It can just be one independent variable. But we are looking at the effect of that one independent variable, simultaneously on 3 different or 4 or multiple outcomes. So it's a method of modeling multiple responses or dependent variables with a single set of predictor variables. So if you just look at this particular narration or sentence here, that's exactly what multivariate analysis means. On the other side, multivariable analysis is used to describe statistical models with one, this time around, it's just one dependent variable, but plenty independent variable. So you can have X1, X2, X3, even as far as Xn, and then their effect on just Y. So that is multivariable. That's the keyword, multivariable. Whereas the multivariate is talking about the dependent component, the multivariable is actually having emphasis on the independent component. That's the difference. Look at this chart here. So look at this one. This is multivariate. This is multivariate. Level of education, we are looking at the effect on the life satisfaction and at the same time, job satisfaction. So this is X, this is Y, this is Y, this is Y1, Y2. And level of education here on the univariate is just 1X, 1Y. And I have some examples on this side. What is the effect of gender, race, and parental income? Gender, race, and parental income, those are 3 different independent variables on both maths and English score. So maths score is a separate outcome. English score is another separate outcome. There are 2 different outcomes. That is for a multivariate analysis. On the other side, univariate. And for the univariate, I still have the same 3 independent variables, but this time around, I'm just looking at the effect on one outcome. That's just the English score. Please don't mix it up. Sometimes it can be a bit confusing. So regression analysis, let's continue. We want to look at the linear regression model. We look at the regression coefficients. We understand and look at the assumptions for a regression analysis. We are going to be able to predict the response variable, and we look at SPSS outputs and comment on the SPSS output. So regression analysis is a very powerful tool in statistical analysis in predicting the value of one variable when we have the value of another variable, especially when those variables have some level of correlation. I go over it again. It's a very powerful tool in statistical analysis in predicting. So you can see where it comes in, predicting or estimating. You want to estimate what might happen in future. You want to estimate the value of one variable given the value of another variable, especially when those variables are related to each other. The assumption is that there should be some actual linear relationship, that there should be correlation, okay? Linear correlation. And another assumption is that the relationship between the dependent and independent variables, they remain the same till the regression equation is calculated. That's another assumption. We also have another assumption that the dependent variable can take any random value, but the independent variables are fixed. And we have this other assumption that we have only one dependent variable in our estimating equation. However, we can use more than one independent variable. Now, I put an asterisk here to let us know that if it were a multivariate, regression, that means that we can have more than one dependent variable. That was why I put the asterisk here, But naturally, most regression equations, just one dependent variable. But in a multivariate regression, we can have two or more, or more independent. What happened?
Okay.
I noticed that it just went off. Let me go back, please.
Okay.
Yeah, I was trying to write something. I don't know what I did that took it off. I think we are on. Am I right?
Yeah, yes, sir. Thank you.
Sorry. Okay. So the advantages of regression analysis: it provides estimate, like I said, estimates of one value given the value of another value. It helps in obtaining a measure of the degree of association or correlation. So part of the analysis we see in regression analysis is correlation. It comes as part of the analysis in regression analysis. And even some of them come with ANOVA. That is why we needed to first tackle correlation and ANOVA before coming to regression. So what is a model? Because regression analysis is a model, a predictive model, something to estimate. So a model is a thing that you follow or use to imitate, or a mathematical representation of relationship. And this is where regression analysis comes in. It's a mathematical representation of relationship. This is a model of a house. Maybe an estate real agent wants to build a house and is showing you how it will look like. So you have something to work with, a model of a car, a model trying to show off a kind of design, and this is our model for our DNA. So regression models, they just like give us the relationship between one dependent variable and independent variables. It can be more than one. So it's an equation that sets up that relationship, and we have our dependent variable as being numerical, and our independent variable can either be numerical or categorical. It's not sacrosanct because our dependent variable can also be categorical, as we will see. So it's not sacrosanct. And we use regression mainly for prediction and estimation, like I said earlier on. So let's look at the types of regression, the regression model. It can be simple regression model or simple regression where we have one independent variable, or it can be multiple where we have more than one independent variable, two or more. And the simple regression can be linear, or it can be non-linear. By now, you know what linear is. Non-linear is when we have curvilinear, when it is quadratic or exponential. And the same thing for the multiple regression, it can be linear or non-linear. The one that actually concerns us in this class is the simple linear regression. Simple linear regression. And that's the one we are going to be looking at, the one in yellow here, the simple linear regression. So in simple linear regression, we predict scores of one variable from the scores of a second variable, and that is one independent variable, to predict our dependent variable. The variable we are predicting is called the criterion variable, or the dependent variable, or the outcome variable. So all these are synonyms that we spoke about in our first class. And the one we are basing our prediction on is the independent variable, or the predictor variable, or the treatment variable. I think we have other names, but those are just synonyms, and we refer to that one as X. And since we said one of our assumptions is that there's a linear relationship between X and Y, that brings us to the equation of a straight line, where we say Y equals to, we say Y equals to A plus BX. A here is our intercept, B here is our gradient. We can say Y equals to B0 plus B1 X. It's still the same thing. Don't let the change of the constants or the alphabet make it look difficult. This is the same thing as this, is the same thing as this. It can be written anyhow. In this particular equation now, our B here is our intercept, where our M here is our gradient. So the way it is written does not matter. What matters is that it is the equation of a straight line, okay? So that is that. So this is the model. This is the regression model. Remember, we were talking about what a model is. This is the regression model for a regression equation, where our Y is the dependent variable, the response variable, the criterion variable, the outcome variable. Those are synonyms. And for example, hypertension. Our B naught here is our intercept, which we say that is the place where our line hits the Y-axis. This is our X-axis. So the place where our line hits the Y-axis, that's our intercept. Don't forget that, okay? And our B1 is the gradient, the slope, which we call it dy dx. So we have something like that. That's our B1. The value of dy over dx is our B1, okay? And is the coefficient that we are always going to be calculating. Our E here is an error margin because the regression model is not a deterministic model. Rather, it is a probabilistic model, meaning that there can be some errors here and there. And that is the E1 that we have there, random error. Awesome. Okay, so these are the coefficient equations. This is the one that we have as normal straight line equation. Now, don't let these small caps on top, don't let it look as if it's confusing. Those small caps here just denote the fact that this is an equation for a sample. This is an equation for a sample. Those small capsules that, okay, for a sample, remember, we are working on sample to make inference on the population, to make inference. So this is the population, this is the sample. So we work on sample to make inference on the population. Now, the formula for the gradient is this, and that's one type of the formula. There's another formula. And the formula for the intercept is the mean of Y minus the gradient times the mean of X. All this will become clearer as we continue. So these are the formulas that we'll be working with, in calculating our regression equation manually. And then we'll look at SPSS outputs. This is another formula for the gradient. And this is just something like XY, minus summation X, summation Y, divided by N, everything minus summation X squared minus summation X, this one squared over N. So this is what that formula is showing. All those other notations is making it look a bit complex, but it's a very straightforward formula. And this is the formula we'll be using because this one is very straightforward. So when we have our X and Y, our values for our X and our values for our Y, this is the kind of table we generate, especially for a simple linear regression. We have the values of X, it comes down that way. The values of Y, it also comes down that way. X squared, which is this squared, Y squared, this squared, and the X times Y, which is what we have here. And down there, we have the summation of the X value, summation of the Y value, X squared, we have the summation, the same thing here, the same thing here. So we have a very good example as we continue. And I told us that is our regression model, that's the equation, where our slope is the estimated change in Y by the slope for each 1 unit increase in X. So this sentence might be looking a bit confusing. When we get to the class example, it becomes clearer, okay? But by now, you should know what our intercept is, the value of Y when X is 0. So if our X here is 0, that means everything here is 0. That means Y will become our intercept. the value of y when x is 0. But this particular narration I will explain as we start with our class example. So look at this particular class example. And I want you to look at the way the research question is phrased. So if you have a research question with this kind of arrangement, then you are talking about a regression, most likely. Look at number 1. What is the relationship between mother's estriol level and birth weight using the following data? So this is the data here. Now, the estriol level is a hormone that mothers have, and it's something that has to do with, gestation, that's children developing in the womb. Okay, so another question says, does estriol predict the birth rate of children? What is the effect of estriol level on the birth rate of children? So all this is showing that you will need something to be able to assess that relationship in an estimation, that's regression. So here we have our X, which is the hormone from the mothers, the milligram per day that is produced. Here we have our Y, which is the birth rate of the children. And as you can see, they are all like just hypothetical. It's not something that is actual, So we have our X. When X is 1, Y is 1. When X is 2, Y is 1. When X is 3, Y is 2. Likewise like that. So this is our X value and our Y value. And we'll just put them, start with our scatter plot. By now, you should understand how this particular correlation looks like. You can see, if you try to put like a circle around it, that it is positive and it's moderately strong based on what we did in correlation in scatter plot. So that one shows that assumption is fulfilled. There's a kind of correlation between X and Y, the birth rate and the estriol level. And then we can populate our table, the one I showed us earlier on. This is our X. When X is 1, our Y is 1. This is X squared for the value of X. This is Y squared for the value of Y. And when we multiply the two, we have that, and it comes down like that. And all these are the sum. So 1 plus 2 plus 3 plus 4 plus 5, 15. For Y, we have 10, 55 for X squared, 26 for Y squared. The total of X and Y is 37. And from here, we can find the value of X bar. This is the mean of X, and Y bar. X bar is 10, 15 divided by 5. That's 3. Our Y bar is 10 divided by 5. That's 2, because we need that in another of our formulas. As simple as that, okay? So we are going to find the gradients. That's the coefficients. We are going to find the gradients by putting in the values that we have here into that equation. And when we do that, as you can see here, our summation xy is 37, our summation x is 15, summation y is 10 divided by 5. Our n is 5. We have 5 observations, okay? And then 55 is the summation of x squared, 15 is the summation of x squared divided by 5. By the time you calculate that, we have 0.70. So our beta 1 is 0.70. We will now put that in the formula for calculating our intercept. Remember our y, the mean of y we calculated earlier on is 2. The mean of x is 3. So we have the value of our gradient from here as 0.70. When you put that there, we have minus 0.10. Remember, our equation is y equals to beta naught plus beta 1x. So we can just say our y equals to our beta naught here is minus 0.10 plus 0.70x. That's our model, regression model. It's just by bringing in those values and putting them there. So like I said, that I'm going to use this example to explain. So our slope, that's our B1. For our slope, that was 0.70. Our y, that is our birth weight for the children, is expected to increase by 0.7 units for every 1 unit increase in the value of X, which is the hormone estriol. Our birth weight is expected to increase by 0.7 units for every 1 unit increase in our estriol value. Our intercept, we understand what that is. That is the value of Y when our X is 0. But here, it's difficult to explain because you can't have the value of a child weight to be minus. But that is what it's supposed to be. Okay, so look at this example now. This is the equation I wrote in the previous slide. That's our regression model. We can predict the value of y, that is the birth weight, from any score of x by plugging it into that formula. So for example, what would we expect the weight of a baby to be if the value of the mother's hormone, of estriol hormone, is 10? It's just by putting 10 where our x is here, and once you put that 10 there, you have 6.9 as the weight of the baby if our hormone is 10. So that is why we say we can use it to predict or estimate, given the value of one variable. So once we have any value of x, we can predict the value of y. So it's just by plugging in the value of x into the formula, and then you calculate your y. And so our new weight now is 6.9 if the mother's hormone level is 10. As simple as that. Now, that same table, that same analysis, those values, I have plugged it into an SPSS, and I have calculated it, and it takes just less than 2 seconds, and it gives us our R squared, which by now we should understand, what it means, and that's the coefficient of determination. I remember we spoke about that, and what it means, coefficient of determination. But this is the output for a regression analysis, and we'll look at it quickly. Look at model here. Constant, that's our beta naught. It gives us the value, which was the same thing that we got via the classwork, minus 0.10. So whenever you see constant in a regression analysis, it means the intercept. And estriol, that's our x. Our value for the gradient is 0.70, which was what we got in the previous classwork. You understand? And then we have the standard error and the coefficient of standardized coefficients. We have the t-value, we have the significance. As you can see here, it's not significant. That is for the constant. But the estriol is significant. It's less than 0.05. And if you look at the confidence interval, it also agrees with that, unlike the upper one that has negative and positive. So this is what you see in a regression output using a software. And you can see that, it's the same thing with what we had, with our classwork. And then you can now interpret depending on how you have crafted your hypothesis. So by virtue of this p-value, you are going to reject your null hypothesis, and then you go with your alternative hypothesis, and then you are done with your study. By the way, the R squared, which we said is the coefficient of regression and coefficient of determination, using this one to interpret now, we mean that 81.2% of the birth weight of children is determined by the hormone level estriol of the mother. That is just the literal interpretation. Other things can now add up to the remaining maybe 17 or 18% of the birth weight. But 81.7% of the birth weight of the children is determined by the hormone in the mother. That is what R squared means. But remember, all these figures are just hypothetical. All these figures are just hypothetical. Now, for the standardized coefficient, it has a similar interpretation. I have it in the next slide. In regression, a standardized coefficient, also known as a beta coefficient, indicates how many standard deviations a dependent variable changes for every one standard deviation change in the independent variable. It's something similar to the gradient. For example, a standard coefficient of 2.25 means that one standard deviation increase in the independent variable results in a 2.25 standard deviation increase in the dependent variable. We don't need this one to a large extent when we are reporting our result, but it's just for A students in case you want to know what that means. And I've spoken about the coefficient of determination R squared, which indicates the percentage of variance in the dependent variable accounted or explained by the variability in the independent variable. So its R squared measures the proportion of variation in Y that is explained by the variation in X, which I've explained before. That is 0.817. And I've told you it's 1.7% of the weight of children is explained by the hormonal level estriol in the mother. And R squared can take any value between 0 and 1. The maximum explanation is 100%. You can't explain more than 100%. And you can have 0 to show that it doesn't even have any form of effect on the dependent variable. This is another class example. Where here you are a Fulani herdsman in Kano, and you are rearing a cow, and you gather the following data. So this is your X. Remember, we are still on simple linear regression, where we have X having an effect on Y, and this is your Y. And now you have one cow. When you give the cow 4 kilograms of grass or food, it brings a yield of 3 liters of milk. When you give the cow 6 kilograms of food, you have 5.5 liters of milk yield. Likewise, like that, till you give it 12 kilograms of food, and you record 9 liters of milk. And the question is, what's the relationship between the cow's food intake and the milk yield? Like we have done in previous classwork, the first thing to do is to do a correlation, which we can do with a scatter plot. And you have it there. You have the correlation there. And if you look at the correlation, you can see that it's also a sort of very strong correlation. The more the milk and the more the food, the more the milk. So there's a strong correlation between the two of them. And then we can populate our table like we did with the previous one. Here we have our X. This is summation, like I told us. And then we can find our mean of X. That is 32 divided by 4. I think that is 8. Our mean of Y is 24 divided by 4, and that is 6. And then we have the total of all the others. We can now plug these figures into our formula. And when we plug it to our formula to calculate our gradient, we have 0.65 as our gradient. And plugging in that value to calculate our intercept gives us 0.80. Our Y is intercept plus gradient X. So I can say Y equals intercept is 0.80 plus 0.65X. This is our regression equation. So for any value of X that I have, I can know the value of Y. That's our regression equation, you know. So our milk yield, that is, if we are interpreting it now for our gradient, our milk yield is expected to increase by 0.65 liters for every unit increase in food, 1 kilogram increase in food. And our intercept here is saying that when there is no food at all, when X is 0, we expect to still have, 0.8 liters of milk. That is just the interpretation of that regression equation. So we have the equation there, and we can calculate what the milk yield will be if the cow was giving, for example, 15 kilograms of food. That means that this 15 kilograms, we just put it here in our X, and that will tell us the milk yield we expect to see if we give our cow 15 kilograms of food. That is regression for you. It can estimate or it can predict. So doing that now tells us that if we give 15 kilograms of food, our milk yield is expected to be 10.55 liters. And this one too, we have it in our SPSS. I just brought out the particular one for the regression, where you can see the constant, which is our intercept, 0.8, and our food, which is our gradient, 0.65, like we got in the previous classwork, And you can see here that our p-value is significant. So you can reject your null hypothesis for whatever way you have crafted your null hypothesis, and you go with your alternative hypothesis. Beautiful. Now, for all we have been talking about is the simple linear regression. Now we want to start looking at the other variants of regression. That is the multiple linear regression, the logistic regression, many of you have heard of that, multinomial regression, and ordinal regression. So let's quickly look at the multiple linear regression in brief. And it's a very simple concept. There's really nothing there. So in multiple linear regression, what we are trying to do is to model the relationship between two or more independent variables. Remember, simple linear regression, it is one independent variable, one dependent variable. Multiple linear regression, you have more than one independent variable, it can be more, even down to n, this is 3. And then you are trying to model it with one dependent variable. Every value of the independent variable is associated with a value of the dependent variable y. So that's just a simple difference. It's just more than one. This is a simple linear regression. X effects on y. In the multiple linear, it's simultaneously considering the influence of multiple independent variables on a particular response variable. The intent is to look at the effect of all these variables while you are adjusting out the influence of potential confounders. I won't be talking about confounders here, but when you have confounders in your, when you want to check for confounders in your data analysis, you use multiple linear regression, because you can now look at those effects individually and knock them off. So multiple linear regression is predicting an outcome Y based on several independent variables, simultaneously. With multiple regression, we form a linear combination of multiple variables. So you are doing them linearly, but you are combining all the effects in one equation, okay? Look at the sample question for a multiple regression. How does an independent variable contribute to explaining the dependent variable after the effect of another independent variable is taken into account? For example, how much does salary contribute to explaining blood pressure when you look at the effect of the number of hours of sleep, of that particular person? So we have blood pressure as our X1, hours of sleep as our X2, salary is our Y. So because we have two now, it's already multiple linear regression. That's just like a sample research question. In simple linear regression, it's a straight line. But in multiple linear regression, it's a three-dimensional space. It's not a straight line again. You can see X1 here, you can see X2 here. But this one is just X, this one is Y. So if there are more, maybe you can have X3 here again. So it is multi-dimensional, and it's a bit challenging plotting. But that's just for you to see the difference, okay? So in simple linear regression, comparing with multiple, we have one dependent. Multiple linear, we also have one dependent. But we have one linear, one independent. In multiple linear, we have a set of independent. In simple linear regression, we have one regression coefficient, one beta 1, because it's only one variable. But in multiple linear, you have multiple, depending on the number of independent variables. If there are 3 independent variables, you have 3 regression coefficients. In simple linear regression, you also have our coefficient of determination, normally written in R, in small letter r. And in the multiple linear, it's still the same thing, but this time around it's written in capital R. They still mean the same thing and it's interpreted the same way. So this is simple linear regression. This is multiple linear regression. You can see beta 1, beta 2. This is also multiple linear regression, beta 1, beta 2, and beta I or beta N, depending on how far. And in all of them, our A is still the intercept. So that's just the explanation of the equation. So this is the regression equation for a multiple linear. Our Y is still our dependent variable. Our A is our intercept. Our B1 is the B2 is the coefficient for X, for variable X, X2. B3 is coefficient for variable X3, and our E is the error term, like I told us, that regression always has some errors that we need to account for. This is the same thing. And let's assume that we have done an analysis. This is how the equation comes out. So that for every unit increase in X1, for example, our Y increases by 3.98 if others are kept constant. And we'll just look at a class example and we'll continue. I told us that our simple linear is one variable independent and one dependent variable. For example, what is the relationship between education, or what is the effect of education on income? Education is X, income is Y. That's a simple linear regression. Now for a multiple linear regression, I can say what is the effect of education, gender, the number of hours you spend at work, and your age on your income. Now you can see that we have 4 different independent variables. I want to call your attention to something. If you look at this now, this is a continuous variable. This is a continuous variable. This is a nominal variable. This is an ordinal variable. It doesn't affect this particular kind of analysis. It works very well, So it doesn't have to be, what's it called? Continuous. However, in simple linear regression, X and Y must be continuous. X and Y must be continuous in simple linear regression. But in multiple linear regression, you can have variations in your independent variables. It doesn't affect your outcome. So this is an example of an SPSS output for a multiple linear regression, where we have here, you can still see our R squared, okay? And then you can see ANOVA, and you can see our sum of squared, degree of freedom, multiple mean square, and whatever. By now, you should be able to understand how to interpret an ANOVA. And this is the table, the output where I'm interested in, where I have told us whenever you see a regression analysis, when you see constant, that is the intercept. When you see constant, that's the intercept. And this is X1, education, number of years in school, age X2, gender X3, hours you spend working X4. So there are 4 independent variables here, and these are their values. Let me see if I can just put out an equation here. So my Y, which is my income, is going to be, my constant is minus 39061.2 plus beta, that's for education, 2785 education plus 341H plus, okay, this is minus 8893 gender, so let me just say sex, plus 844 hours you spend, working. That is my regression equation. So as you can see now, if you put in any value of education or any value of age or any value of number of hours you spend working, it will be giving you the value of Y when other values are kept constant. So it's still a model. It's just to put in those values and then you can calculate your Y. Look at how you report it. When income was predicted, it was found that education in years, I put the beta value, which is that 2,785, p-value, sorry, I didn't even talk about the p-value here. All of them here is only education that is significant. Okay, let's go on. P-value was significant predictor. Age, I put the beta value is not significant. Gender, the beta value not significant. And the time working, the beta value not significant. They were not significant predictors. The overall model fit was 0.5358. That's our coefficient of determination. What does that mean? That means that 35.8% of your income is explained by the educational level, your age, your gender, the amount of time you spend working. There might be other factors that is also explaining your income, possibly the type of work. The type of work is also going to explain your income. So, but for those 4 variables, they explain 35.8%, of your income. So depending on the question you are answering, you might also want to report the regression equation, which is what I have here. You can report the regression equation, or you can put your finding in the table. Now, this table is not for that particular example. I just got this table to let us see how it is. So you have your intercept, which is your constant. You put your individual variables, and then you put the coefficients, which you can extract from the table, the standard error, the 95% confidence interval, the p-value. The word statistics, we'll talk about that as we continue. Logistic regression also in brief. This time around, it is used to examine the association of categorical or continuous independent variables with one dichotomous dependent variable or binary dependent variable. So in logistic regression, your Y is binary variable or dichotomous, which means that it is qualitative. Okay? And here the outcome is normally in probability, and that is between 0 and 1. So in logistic regression, we do what we call a logit transformation, to the odds. That's the probability of success divided by the probability of failure, and we'll talk about that as we continue. This is also known as the log odds or the natural logarithm of odds. Log odds are difficult to explain or to interpret. So we normally exponentiate the beta estimates, to transform the log odds into what we call a odds ratio. Our odds ratio is easier to interpret, and we'll be talking about that as we continue. So this is the equation for, what's it called? For a logistic regression. So this is our Y equals to the same intercept, gradient, and X. So this is our Y, as it were, our dependent variable. It comes in probability. So we are Y, our P is the probability of an event occurring divided by 1 over P, which is the probability of the event not occurring. And that is what we call the odds. And we'll talk about that as we continue. So this is like a sample output of a logistic regression. Don't forget, anytime you see constant, that's your intercept. Here we have 4 different variables: age, weight, gender, and maybe the volume of oxygen or maximum volume of oxygen, whatever that might mean. We have our gradient values here, standard error of the mean, our word statistics, the degree of freedom. This one is 2 minus 1 anyway. And then the significance. And as you can see here, these 3 are the ones that are significant. And it has their odds ratio value here. And we have our confidence interval. Now, in the confidence interval in this particular analysis is not following the rule for a t-test kind of confidence interval. So here you might have a particular one that is not significant. Let me remove the ink. You can have somewhere, for example, this one is not significant. One will have expected maybe a minus and a plus, but this is not a t-test table, and that is why it's not following that particular rule. Okay, so here we have an output for a logistic regression. Our output here, there should be a place where entered. Okay, we don't have the output here. I just extracted this table from the internet, but these are our 4 independent variables. Our dependent variable y is binary or dichotomous. It just has 2 levels of expression. So the word statistic, which I told us about earlier on, this particular one, is named after Abraham Ward. It's a parametric statistical measure to confirm whether a set of independent variables are collectively significant for a model or not. It is used for confirming whether each independent variable present in a model is significant or not. There is a particular value that we look at for the word statistics to say if it fulfills that criteria or not. I think it's between 2 and 5. I've forgotten. But that is what it is. The word statistics is more like this, our coefficient of determination, to tell us, the way the model represents the equation that we have, our regression equation. But that one is something we can check up to look at the particular value of the word statistics that make our model equation significant or not. So the odds ratio that we get, it represents the odds that an outcome will occur given a particular event, compared to the odds of the outcome occurring in the absence of that same event. When our odds ratio is greater than 1, that means the event is associated with a higher odds of generating a specific outcome. When it is less than 1, the event is associated with a lower odds of that outcome occurring. If it is equal to 1, there's no difference. We are going to look at odds ratio as a topic on its own. So when we are reporting logistic regression, this is actually what we report, and with the p-values. This one, the odds ratio is just like 1, 1. This is the one that seems to have, a reasonable figure, and it's still significant. And we'll talk about how to interpret odds ratio as we continue. Don't let me start that here, because it has a kind of explanation that needs to be attached to it. So for the logistic regression itself, remember X to Y, where our Y now is qualitative. So that is where qualitative comes in. For the binary logistic regression, our Y is binary. For the multinomial logistic regression, our Y is nominal. By now, you should understand what a nominal variable is. This is N, nominal variable. And for the ordinal logistic regression, our Y is ordinal or rank ordered. That's just the different types of logistic regression. The binary, the Y is binary, which is still nominal anyway. It's just that for the nominal type, the Y is more than 2 levels of observation or expression. For the ordinal, it is ordinal, rank ordered, either ascending or descending. Now, for the binary, in this approach, it has only 2 possible outcomes. That is the dichotomous variable. It's used when your Y variable can take only 2 variables. Within logistic, this is the most common one that we see. It is one of the most common classifiers for binary classification. For example, you want to assess cancer survivor. The outcome can either be alive or dead. It's no more than that. Will the Labour Party win at the Court of Appeal? Yes or no? It's either they win or they lose. So this is the commonest type of binary logistic regression. There's something I want to say here. X, Y, binary logistic regression. So we can have a multiple binary logistic regression where we have X1, X2, X3, X4, all of them working on Y, where Y is either 1 or 0, 2 levels of expression. So this one is simple binary logistic because it's only one independent variable. We can have multiple binary logistic, just semantics by virtue of the terminologies we are using. In multinomial, this is where our Y, the dependent variable, has 3 or more possible outcomes. These values have no specified order because if they had a specified order, that would have made them ordinal. For example, does educational level, age, peer pressure, and socioeconomic status of a lady affect her choice of a car color? So there are 5 options here. We have red, blue, white, black, and green. All these are different colors. It can even be more than that. So this is the Y part, and it is our dependent variable, and it has 3 or more possible outcomes. Because if it was only 2, then we should be working with the logistic regression, binary logistic regression. For the ordinal, like I said, it's just the same thing. However, in this case, our Y is ordinal. It's ordinal. When the response, this is when the response variable has 3 or more possible outcomes, but it is ordinal. An example of ordinal responses includes grading things from like maybe Likert scale, ranking, predicting result of a sporting event. And look at this class example. Does the type of hospital, the location of practice, the specialty, the gender, and age, does it predict the socioeconomic status of the doctors? And we have classified our Y, socioeconomic status, to either low, medium, or high. So these ones are just an ordinal dependent variable. And if you have a question like that, in your SPSS, you'll be picking ordinal logistic regression for your analysis. So all I've been trying to say now, I have put them in sample research questions. For simple linear regression, we have one predictor, X, we have one outcome variable, Y. And look at this question here. What is the effect of number of hours of study, that's our X, on the exam score, Y? That's simple linear regression. And you can see that both of them are continuous, like I said. Both of them are continuous. For the multiple linear regression, we have 2 or more. Now, the 2 or more does not mean that they have to be continuous. You can have others, maybe ordinal, you can have even nominal. But at the same time, it's still one outcome which is continuous. And look at this example here. What is the effect of the number of hours of study? That is X1, age, that is X2, type of school attended, that's X3, exam scores, our Y. That is the multiple linear regression. Binary logistic, here it can be continuous, but our outcome is binary, qualitative, very important, And it can also be qualitative here. Our predictor can also be qualitative here. Look at the question, what is the effect of the hours of sleep on the survival of a test patient? So hours of sleep is continuous and is our X, one independent. The survival of our test patient is either it survives or it doesn't survive, alive or dead. That's binary. And that's a binary logistic regression. A multinomial, now it's multinomial. We are talking about our Y being nominal, but more than 2 categories. And more importantly, no ranking. And look at the sample question. Does the speed of the vehicle, the type of the vehicle, the age of the patient, and the use of seat belts in a road traffic accident, does it determine, predict the type of outcome? Here, these are the type of outcome: coma, bone fracture, or death. There's no ranking. Any one of them could easily happen. So in situations like this, use a multinomial logistic regression. On the other side, the ordinal logistic regression, we also have 1 or more independent variable. It can be qualitative also. But here, our outcome is qualitative and it is ranked ordered. For example, what is the effect of your age, your CD4 count, your gender, and family support on the stage of HIV? And the stage is ordered from stage 1 to stage 2, stage 3, and stage 4. And then this is the one I spoke about earlier on, that we can have a multivariate. All the ones we've been talking about are multivariable. We can have a multivariate regression analysis where you can have your independent variable that can be 1 or more. Even they can have qualitative as part of the independent variable. And then the outcome is 2 or more, and it's continuous. 2 or more outcome. And look at the sample equation and sample question here. What is the effect of gender, race, and parental income on both math and and English scores? Math score is one outcome, English score is another outcome. And you can have a question like that, where this one is X1, X2, X3. So the fact that we are having two separate outcomes makes it a multivariate regression analysis. I think towards the end of the class, there's sample classwork that we'll do. So let's quickly go through contingency table analysis. We're going to be a bit faster. So these tables, they represent combinations of levels of both independent and dependent variables, which is the same as explanatory and response variables. The numbers in the tables represent counts, and the row or columns, we have the marginal counts. The 2x2 table is the commonest, and it's used for dichotomous variables to compare groups of people. It puts one dichotomous variable across the row, another one across the column, and it's useful in determining association between exposure, and outcome. So this is what I'm talking about. This is a 2x2 table. So this is group 1, and this is group 2. These are the marginal counts. This one here, and this one here. These are the marginal count. So this is the 2x2, A, B, C, D. Where marginal count here is A plus B, marginal count here is C plus D. And for the column, marginal count here is A plus C, marginal count here is B plus D. Where this is the grand total of all the cells, A, B, C, D. Some of the uses include odds ratio, relative risk, attributable risk, absolute risk, Cohen's Kappa, sensitivity, specificity, positive predictive value, negative predictive value. It has a lot of use. I hope we'll be able to go through this ones. It's not that much, and then we'll continue from there. So let's talk about odds ratio. I want us to first know cardinally that when we say odds, it is not the same thing as probability. Please, very important. In the past, I used to make that mistake. For probability, is the proportion of times an event will occur if that observation were repeated many times. And probability is normally between 0 and 1. For example, what is the probability of me putting my hand in my pocket now? I'm bringing out a $100 note. That is 0. I don't have any $100 in my pocket. You get the point. But let's assume that I have $50 note, I have $20 note, and then I have a $100 note. So what would be the probability of picking a $100 note? Is just going to be 1/3, because now it is there. The 0 means that, there's no way, it doesn't exist, okay? So in contrast to probability, odds are simply a different expression of probability. Our odds is the probability of an event happening divided by the probability of the event not happening. That was why we said our odds is the probability of maybe X divided by the probability of 1 minus probability of X. So this is event happening, and this is event not happening. And because it is a ratio, it can range from 0 to infinity. Because it is a ratio, it can range from 0 to infinity. Probability is a proportion, and that is why it can be 0 to 1. Proportion, that's part, but this one is ratio, okay? So look at this example here. I have a bag with 10 balls, and that's the bag with 10 balls. And as you can see in that bag, I have 4 green balls, I have 6 red balls. That's the bag with 10 balls. So let's assume that I share, and the balls are all the same size, the same shape, so that it doesn't make anything. Let's assume I close my eyes, I shake the bag very well, and the question is, what is the probability of me picking a green ball at random? So that will be 4 over the total number of balls that are there, 10. That's 2 over 5. Am I right? Yes. So it is 4 over 10 because I have 4 balls and I have 10 balls in all. That's 2 over 5. That's 0.4. Now, that is the probability of picking a red ball. The next question is, what is the odds? Now, we are looking at odds of picking a green ball. The same bag now. So the odds of picking a green ball is the probability of picking the ball divided by the probability of not picking the ball. And the probability of not picking the ball, like we said, is 1 minus P. So this is P divided by 1 minus P. And our P is 0.4. So that's 1 minus P, that's 0.6. So we have 0.4 divided by 0.6. And that gives us 4 over 6, which is 2 over 3. But let us walk through how we arrived at that. So we have already found that the probability of picking the ball is 0.4. What's the odds? The odds is the probability of an event divided by the probability of the event not happening. The probability of the event not happening is our probability actually of picking a red ball, because it's not a green ball again, and that is 6 over 10, which is 0.4 now divided by 0.6, and 4 over 6, 2 over 3, 6 over 7. So you can see that 0.4 as our probability is not the same thing as our odds. That's what I'm trying to emphasize here. Our odds is different. Please note that even this example that I've been talking about is not odds ratio. It's just the odds that we are still talking about. We have not gotten to odds ratio. So the probability is different from the odds. They don't measure the same thing. They don't report the same thing. Okay, so now let's talk about the odds ratio now. So an odds ratio is the odds of an event happening in one group, over the odds of the event happening in another group. For example, those who go for regular medical checkup divided by the odds of the same event in another group, those that do not go for regular medical checkup. So that means that in odds ratio, you find the odds in group 1, then you divide it by the odds in another group, the group 2. And this event could be it depends on what you are looking at. So for smoking, we could have group 1, maybe group 1 are smokers, group 2 are non-smokers. Alcohol consumption, group 1, they consume group 2. So just like that, and on depending on whatever you are studying. The odds ratio, the odds of an event is the probability it occurs divided by the probability it does not occur. We have discussed that. The odds ratio now is the odds of the event in group 1 divided by the odds of the event in group 2. For example, look at what we have here. So I can say here that group 1 here are smokers. And group 2 here, I can say they are non-smokers. And maybe what am I looking at for? Can I say maybe cancer? So I can say cancer. The event I'm looking for here is cancer. So this one, there's cancer. This one, there's no cancer. And we can definitely end up classifying them or categorizing them in a 2-by-2 table. In a 2-by-2 table. So for example, our probability of an event occurring of cancer among smokers is going to be A over A plus B. That's the probability of, what's it called? Cancer among smokers. That's the probability of the event happening. The probability of not having cancer among smokers, like I told you, is going to be the probability of no. That is B over A plus B. So when we divide it like that, this is what we have here. And you cross out this, you end up with A over B. So our odds for cancer among smokers is A over B. And if you do the same thing for the odds for cancer among non-smokers, is going to be C over D. So this is the odds for cancer among smokers, odds for cancers among non-smokers. Odds ratio is going to be A over B divided by C over D. That's our odds ratio. Let's continue. So we have that, like I said, A over B divided by C over D. And when you cross multiply A over B times D over C, you now have AD divided by BC. So that's just, you cross multiply, that's what you end up. So our odds ratio is just AD over BC. Now, this is a chart showing us the same thing we've been talking about, odds ratio. How be it, they are using some, notations here that is making it look as if it's something highfalutin. There is nothing there. This is A, this is B, this is C, this is D. This is our A plus B, A plus C. This is B plus D. Our marginal counts, if you remember. This is A plus B, and this is C plus D. So it's just, all this formula here is just AD over BC. I just wanted to, because you can come across some write-ups It's the same thing. People use different notations and they make it look as if it's something highfalutin. It's just the same thing. There's really nothing there. So when we do like a study, for example, a cohort study, we have already calculated it. I won't waste time here. Eventually, when you go through all the calculation, you will end up finding that your odds ratio is AD over BC. You know, that is it. The same thing, if you do like a case control study, and then you go through all the calculation, it still ends up to the same thing. Our odds ratio is AD over BC. So what matters importantly for us is to able to categorize our findings in a contingency table accurately, A, B, C, D. Our odds ratio is AD over BC, whichever method you use. And then interpreting odds ratio is very important. Odds ratio is a measure of association. You know, when it is less than 1, it shows that maybe that particular exposure is protective, that the more the exposure, the better for you, so to say. When it is equal to 1, it shows that there's no effect, okay? But when it is greater than 1, it's a bit like causative. You know, we query that, is this what is causing this particular outcome? So please put that in mind. And normally, this one is no effect. We normally assess our odds ratio from number 1. This one is greater than 1. This one is less than 1. And you'll see some sample explanations for us to see. So odds ratio between 0 and 19.99 indicates lower risk, like it is less than 1, okay? And between 1 and infinity indicates higher risk. And when it is equal to 1, it shows that there's no relationship. For example, when we have an odds ratio of 0.75, what does that mean? And please look at this particular bullet, very important, very important. When you're interpreting an odds ratio or any ratio, like relative risk, like hazard ratio, odds ratio, any ratio for that matter, it is helpful to look at how much it deviates from number 1. Please, very important. So for example, an odds ratio of 0.75 means that it is less than 1, okay? So in one group, the outcome is 25% likely. This is how much less it is from 1. So here we'll be reporting an odds ratio of 7.5 that maybe a particular group where we have that odds ratio, you know, it's 25% less likely to come out with an outcome of interest. It's 25% less likely to come out with an outcome of interest. And an odds ratio of 1.33, we still check it from deviation from 1. That means it has 33% more likely. Okay, one group has 33% more likely. So always interpret it in relation to number 1. It makes it easy for you. If the odds ratio of illness between male and female, for example, is 0.4, it means that your exposure is protective, you know, for females. Why? Because it is less than 1. Yeah. And what is the degree of protection? 60%. And I think you understand how that is. Because 0.4 is about 0.6 away from number 1. Sorry, like this. Is 0.6 away from number 1. Look at this example again. How do you interpret odds ratio of 0.25? To start with, it is less than 1, so it's protective. But what is the degree of protection? It's about 0.75% away. That's 0.75 away from number 1. That means that those who are having that odds ratio, they have 75% lower or protective, you know, benefits compared to those who are exposed for a particular outcome of interest. Don't forget, always rate it, you know, in relationship to number 1. Look at this example. I have 250 commercial sex workers in Enugu, and we have the following data in contingency table. That's 2 by 2. You know, their cigarette use and their alcohol consumption. This is cigarette use, this is alcohol consumption. And I want to see the odds, you know, that the commercial sex workers who smoke will also take alcohol. So from here, this is our A, this is our B, our C, our D. That's what we are trying to look for now. So for those who smoke, the odds of using alcohol is 100 over 45. Remember, our odds here for alcohol use is A over B. Our odds among those who don't smoke and taking alcohol is going to be C over D. And our odds ratio is just a division of the 2. We can go via this route, or we can, cross multiply, like I told us earlier on. So let's just look at two methods. So for those who smoke, the odds of using alcohol is 100 over 45, that's 2.22. For those who don't smoke, the odds of using alcohol is 40 over 65, that's 0.65. So our odds ratio is 2.22 over 0.65, that is 3.6. The estimated odds that commercial sex workers who smoke will also take alcohol is 3.6 times the estimated odds that non-smokers will use alcohol. So we can say that commercial sex workers who take cigarettes have 3.6 times more odds, of taking alcohol. That's just the interpretation of that, And that same example, like I said, we can just cross multiply 100 times 65 divided by 40 times 45, and you have the same value. So that's odds ratio. It's a very straightforward calculation. Another example here is alcohol consumption and development of liver cancer. So here is exposure. It takes alcohol, does not take alcohol. Here is our outcome. So I can say liver cancer. This is present liver cancer. This one control, they don't have liver cancer. We have our A, B, C, D. What's our odds ratio? What does it mean? So we can just cross multiply 160 times 110 divided by 40 times 90. Now you have a figure, 4.89. So our interpretation says the odds of liver cancer is 4.89 times greater among those who consume alcohol compared, we have to finish that sentence, compared to those who do not take alcohol. So this has an implication. We can now go out and start making noise on the media that people should reduce their alcohol consumption, blah, blah, blah. That's what it means, and that's how we conclude our finding in that area. Recall how we interpret our odds ratio. We said it's a measure of association, and if it is less than 1, we look at it that it is protective. If it is 1, there's no relationship. If it is greater than 1, we say maybe it is causal, although not conclusive. Okay? They are most commonly used in case control studies. However, they can be used in cross-sectional studies and correlational study designs, and the safest strategy for odds ratio is that we should limit their use to case control studies and logistic regression. So now, in our logistic regression, like I mentioned earlier on, when you go to your exponential B, and you see a value of odds ratio there, you should be able to interpret what it means in regards to your dependent variable. Whatever value you see now, you can interpret what it means in regards to your dependent variable. Quickly, we look at relative risk, attributable risk, absolute risk. So relative risk is used when you are comparing outcomes of those who are exposed to something, comparing them to those who are not exposed to something. It's similar to odds ratio, but it has a different approach. And we normally use them in prospective studies, like in incidence studies or, when you are doing a cohort study. You cannot calculate them in case control, because in case control, we don't have the population. That's the entire population that is at risk of that condition. You can see it's still a 2 by 2 table, and our relative risk is the ratio of incidence of the disease in those who are exposed over the incidence of the disease in those who are not exposed. And I will give us a small example. So let's assume that we are working with malaria. And then our exposure is that this one, they use insecticide treated mosquito net. But these ones, they are not using. So that's our exposure. Our exposure is the mosquito net. And these are the number of people that have malaria, when they still use the net, and these are the number of people that have malaria when they don't use the net. These are the total number of people that use the mosquito net, total number of people that don't use mosquito net, total number of people that have malaria, total number of people that do not have malaria. The same thing, these are our marginal counts, So here we can find our incidence of the disease in the exposed. Incidence of the disease in the exposed is just A over the total number of exposed, A plus B. If you look at that, this is probability, but we are not talking probability. Incidence of the disease in those who are not exposed. So if we're having, that's the malaria in those who are not using mosquito net, that is C over C plus D. That is the incidence of disease in those who are not exposed. This is exposed, this is NE, not exposed. Our relative risk is just dividing the up with the lower one, as simple as that. So like A over A plus B, C over C plus D, relative risk is that, incidence in exposed divided by incidence in unexposed. And that's the formula. Risk, that incidence is the same thing as risk. Remember, relative risk. So that is where the word came from, okay? And this is an example. A follow-up study in JOS on the use of condoms among 75 men and the development of sexually transmitted disease shows the following in cross-tabulation. See the study, follow-up, a cohort study. So these are those who are not using condom. These are those who are using condom. Invariably, these are the ones that are exposed. So we can choose any group as our exposed or unexposed, depending on how we phrase our research question. So here we have 21 people having the sexually transmitted disease, 28 do not have, and they are not using condom. We have a total of 49 here. Those who are using condom, 2 of them have the disease, 24 do not have the disease. So we have 26 here, okay? And we are asked to calculate the relative risk, for the occurrence of STD among those who don't use condoms. So these are the reference group you are working with. And we can calculate even from here. This is just going to be 21 divided by 49 for the incidence among those not using condom, and then 2 divided by 26 for the incidence among those who are using, condom. And once we find the ratio, we have our relative risk. So you can see it here, and then we have our relative risk as 5.57. Remember the interpretation when we are looking at odds ratio, how you interpret ratios. We look at it from how far away it is from number 1. That means that those that are not using condom, they have about 5.57 times more chances, more risk of having sexually transmitted disease compared to those who are using condom. That is how we end up with our public health messages after we have done this kind of calculations. So we now go out and start campaigning that people should ensure they have protected sexual encounters because it will reduce their chances of ending up with sexually transmitted disease. Okay, so like I said, it's similar to the odds ratio. If it is greater than 1, the risk is higher, or we can say it's causative. If it is equal to 1, there's no association. If it is less than 1, it means that the exposure reduces the risk of acquiring the outcome or the disease. So a relative risk or odds ratio greater than 1 indicates, okay, it's just the same thing, okay? So for example, a relative risk of 1.2 means that those exposed, they have 20% more likely to be diseased. 1.4, 40% more likely. The same thing with odds ratio. 1.2 means that the odds of the disease is 20% higher in those exposed. However, a relative risk of 0.85 automatically is less than 1, okay? So, and that means that it's a bit protective. A relative risk of 0.85 corresponds to a risk reduction of 15%. Why? Because 8.5 is about 0.15 away from number 1. Remember that cardinal way of interpreting them. It was 0.15. So it has about 15%, reduction in risk. Therefore, those men that do not use condom have 5.7 times the risk of having STDs compared to those who use condom. So we advise people to use condom. Another example, this is another 5 years follow-up study of an oral health survey in Kano State on the use of fluoride-containing toothpaste among 75 students. And we are trying to look at the effect of that on tooth decay. So these ones, they brush with toothpaste containing fluoride. This group brush with toothpaste not containing fluoride. So I can say these ones are exposed, these ones are not exposed. And these are our outcome, yes, no. Tooth decay, no tooth decay. So among those who are exposed, this is 26. We have 2 of them developing dental caries despite using the fluoride-containing toothpaste. This one is 49. Among those who are not using fluoride toothpaste, 21 of them develop tooth decay. You understand? And we want to look at the relative risk. It's just the same thing. So we first find the incidence of tooth decay among the exposed. That is 2 over 26 divided by 21 over 49. That will give us our relative risk. So let's continue. So this is our sample research question. What is the relative risk for the occurrence of tooth decay among students in Kano who use fluoride-containing toothpaste compared to those that don't use fluoride-containing toothpaste. And we have our A, B, C, D, okay? And then I've just done the calculation there, 2/26 divided by 21/49. We have that, and it comes here. And as you can see from that value, it is less than 1, which shows that it is protective, by default. Now we want to know how much protection it is. I can tell you that it has 82%. That is 1 minus 0.18. 1 minus 0.18. That's about 82%. So I can tell you that patients, students that use, or people that use fluoride-containing toothpaste, they have 82% less risk of developing tooth decay compared to those who don't use fluoride-containing toothpaste. That is how it works. That is how you interpret it. We have said that if it is less than 1, or if it is greater than 1, it's positive. If it is equal to 1, there's no association. If it is less than 1, it means that exposure reduces the risk, okay? Therefore, those students that use fluoride-containing toothpaste have 82%, that's 1 minus 0.18, less risk of having tooth decay compared to those who don't use fluoride. So it makes sense, it's logical, So the lower the, the lower the neat one, the stronger their benefits, for public health use. Attributable risk is the amount of disease that can be attributed to a certain exposure. The amount of disease that can be attributed to a certain exposure. The difference between the risk in exposed subjects and unexposed subjects is called attributable risk. If the risk of lung cancer among smokers is 7.6%, and in non-smokers of the same age and gender, it is 1.2%. The risk attributable to smoking among that population is 7.6 minus 1.2, that's 6.4%, okay? And it is just the same thing as risk difference. Remember when we were talking about relative risk, we had incidence in exposed divided by incidence in non-exposed. So our risk difference is just incidence in exposed minus incidence in non-exposed. That's just a simple attributable risk. And for it to be valid, it is necessary that they are similar. The groups that you are comparing. That means there is no other factor that can alter the risk apart from the default factors among the two groups. So attributable risk is the amount of risk that can be ascribed to the exposure. That means that if you remove that particular excess risk, it reduces the chances of developing a particular outcome by virtue of that value. So it's the difference in incidence in those with risk factors and those without. Let's continue. So going back to that example of the use of condom and not using condom, the incidence of disease among those who do not use condom, is, 0.42. The incidence of disease among those who use condom is 0.07. Our attributable risk, like I said, is the incidence in the exposed minus incidence in the non-exposed. And if you do that, you have 0.3519. We convert that to percentage. So what this is telling us is that 35.2% of STDs in the studied population are as a result of not using condom. 35.2% of STDs in the studied population are a result of not using condom. So we can attribute 35% of STDs to the lack of using of condom in that particular population. And so if we introduce condom into that population, we have knocked off the tendency of developing STDs by 35%. So we can attribute STDs in that particular population to not using condom. That's what we call attributable risk. So this is the risk in exposed, risk in non-exposed. That difference is attributable risk, okay? The same thing here, the exposed group and the unexposed. That difference is the attributable risk. So it measures the impact that the removal of a certain factor may have on the incidence of a disease. It also measures the strength of association. The higher the relative risk, the greater the association of the factor to the disease. So when we have a high relative risk, it's normally suggestive of etiology or causality, but it is not always, okay? It's not always. So in summary, relative risk and odds ratios are important as measures of the strength of association. Attributable risk is a measure of how much disease risk is attributed to a certain exposure. It's very useful in determining how much disease can be prevented. So relative risk is valuable in etiological studies of disease, while attributable risk is useful for public health guidance. All this health announcements on how to reduce maybe the development of some exposures. Absolute risk of a disease is one's risk of developing a disease over a period of time. We all have absolute risk of developing all manners of diseases in the world, but this risk can be expressed in different ways. For example, you can say 1 in 10 risk of developing a certain disease, or it can be in percentages or in fractions, 10% or 0.1 risk, depending on whether you are using percentages or decimals. So the chance or probability of someone in a group experiencing an outcome is what we call an absolute risk. And how do we calculate that? The number of people with the condition, the total number of people in the group. It's just more like incidence. It's just more like incidence, okay? Relative risk is just a ratio of those with the condition in one group compared to those with the condition in the other group. The groups you are comparing to should always be at the bottom of that, should be the denominator of the fraction. Look at this example. 22,000 doctors were randomly assigned to be taking aspirin or placebo. Placebo is something that has no medicinal effect, just blank, okay? And then they were observed over 8 years, and they were checking to see the development of heart attack. 22,000 physicians. So these are exposed. These are not exposed. And out of the exposed, 104 of those who are taking aspirin developed heart attack over 8 years. 189 of those who are taking the blank medication developed heart attack over 8 years. And these are the total. These are the total and the total of the whole number of people. The question here says, what's the absolute risk of someone in the aspirin group having a heart attack? That would just be 104 divided by the total number. And likewise, for those in placebo, it's going to be 189 divided by the total number. That's the absolute risk. And we have it there, So for those in aspirin, you have 0.0094. That's their risk of developing heart attack. And those who are not taking aspirin, 0.0171, okay? So it now asks the question of what's the relative risk now of someone in the aspirin group having a heart attack compared to the placebo group. Let me just go back. It will just be this particular value divided by this particular value, because this is the incidence in exposed, this is the incidence in unexposed, okay? And we can also swap it, by putting the placebo on top compared to those in aspirin. That's for C and D. So let's look at it. So that's what I just said. And we have 0.55. As you can see from here, it is less than 1. And theoretically, it tells us that it is protective. That means taking aspirin protects you from the tendency of developing a heart attack. And here I can tell you that it has a 45% protective value. How did I get 45%? 1 minus 0.55. Remember how we interpret ratios. And here, the relative risk of someone in the placebo does not have any active agent compared to the aspirin is greater than 1. That means that it has some kind of association or causative, and this one is about 81%, it's 1.2, like 82% higher. They have higher risk of developing heart attack compared to those who are taking aspirin. Let's continue, and I want us to know that even if we are having our relative risk, it cannot be negative. We have discussed about how to interpret them, and I want us to look at the values. So the first one where we got 0.55, I said it is about 45% less risk to have a heart attack compared to those, who are taking placebo. However, for the other option where we had 1.819, I said that there are 82% more risk to have heart attack compared to those who are taking aspirin. That means aspirin is a good, preventive measure of developing heart attack. So it is desirable to have relative risks which are greater than 1, as it is easier to interpret what they mean compared to when they are less than 1. Anyway, based on what we have discussed, it is easier to interpret all of them. So from epidemiological perspective, Absolute risk is the same as incidence, like I said. You know, that is the rate at which new cases arise in a population during a certain study period. So relative risk is the ratio of two incidents in exposed divided by incidence in unexposed. And prevalence is the proportion of the population that has a certain condition. Let's quickly look at Cohen's Kappa. I think that's the one we'll look at as the last example under contingency table analysis. It's also referred to as Cohen's general index of agreement. Many times you want to do a study and then you need to train or recruit a research assistant to help you collect some data. It is good you do this measure of association to ascertain that your research assistants are doing the right thing. You need to check their inter-examiner reliability. This is one method of doing that. It was originally developed to assess the degree of agreement. So you can see, you use it to assess the degree of agreement between two judges or raters or examiners or researchers on the basis of a nominal classification of two categories, that's contingency table. So the Cohen's Kappa coefficient is a statistic that is used to measure inter-rater reliability. So you want to check an agreement between people's measurement for qualitative items. It is generally thought to be a more robust measure than simple percent agreement calculation because our K, that is the coefficient, it takes into account the possibility of agreement also occurring by chance. As you can see here, we have two examples, and we have an example here. I just want to take us back to our contingency table, A, B, C, D. Okay, so we have Inspector A, we have Inspector B. So let me assume that this is Dr. Lawal, you know, and he has trained me on a particular assessment, and we now have a number, maybe like 80 assessments, you know, to go through. He has trained me, and then we went to the field to look at 80 people and to check their assessment as either good or bad, good or bad. In 33% of all the assessments, we both agreed that, no, yeah, in 33%, where I can just say this is 100% anyway, we both agreed that they are both good. However, in 13% of those assessments, Dr. Lawal said they were good, but I said they were bad. That's a kind of disagreement. In 7%, he said they were bad, but me, I assessed them as good. However, in 47%, we both agreed that that assessment was bad. So we have agreement between A and B. That is 33% and 47%. But in this C and D, we disagreed. So how do we now know if my measurement agrees in general, you know, with Dr. Lawal's assessments? Can Dr. Lawal now tell me to go out and collect data by virtue of this agreement? Is it acceptable? If I go out and I come back with data, will it align? Will it agree? Is it presentable? Can we receive it? Can we take it as being authentic? That's all I'm trying to say. So it's a measure of association of nominal variables. So for this measure of association, it requires that we calculate two values. The first one is PO, and that is the proportion of cases in which agreement occurs. So in our example, let me just go back and remove this ink. This is where our agreement occurs. Here we both scored good, good. Here we scored bad, bad. So we can add it up. That's 0.33, 0.47. That gives us 0.80. Okay, so that is the first one, PO. And that's how we got 0.82. That's A plus D. The other thing we need to calculate is the PE, and that's a small formula there. And that's the proportion of cases in which agreement would have been expected due purely to chance, based upon the marginal frequencies. So our PE is PA times PB, QA times QB. Let's go back. So this is PA times PB, QA times QB. So this is the value. We will multiply them. That's the marginal values. You know, that's for calculating our PE, which we have here. So you can see here, that's A plus C times A plus D, plus B plus D times C plus D. And these are the marginal, this is A plus C, as you can see, 0.33 plus 0.13, that's 0.46. You multiply it by this, and then we multiply this by that. Okay, so, and this is the formula for Cohen's Kappa. Let me just go back. If we calculate our PE, we are going to get 0.508, and then we impute it into this formula. Our PO is 0.8. We have calculated that, minus our PE divided by 1 minus PE. And when you do all the calculation, you end up with 0.59. Now, what does this mean? We have a table that tells us what it means. If we had gotten 0, it shows there's no agreement. I'm just doing my own. Dr. Lawal is on his own too. But between 1.0 to between 0.1 to 0.2, slight agreement, 0.21 to 0.4, fair agreement, 0.41 to 0.6, moderate agreement. This is where I fall, because I think our calculation here is 0.59, moderate agreement. But if it was 0.61 to 0.8, substantial, 0.81 to 0.99, near perfect agreement. If it is 1, that's 100%, that's perfect agreement. However, you should always aim to have a score within this range, because that is where we can be sure that what I am doing is what you are doing. I can send you out to collect my data without any fear that you are collecting rubbish. Let's look at a class example. Medical researchers are interested in evaluating the efficacy of a new treatment for a skin condition. So there's a new treatment and there's a skin condition. So dermatologists from participating clinics were trained. Dermatologists are doctors that take care of the skin. They were trained, so you can see there's a training there, to conduct the study and to evaluate the condition. After the training, 2 dermatologists examined patients with the skin condition from a pilot study, and they rated their findings. So this is dermatologist 1, and this is dermatologist 2. So for the particular skin condition, both of them agreed in 29 occasions that the condition was bad, both dermatologist 1 and 2. But in a particular case, dermatologist 1 was saying that it was bad, and then in 15 cases, dermatologist 2 was saying that it was good. So this is discordant. There's no agreement here. In another case, dermatologist 1 said that it was good, where dermatologist 2 said that it was bad. That's for 8 cases. However, both of them also agreed in 36 conditions that they were both good and good. And the question is for us to see if there's an agreement between the 2 of them. Remember our formula. We need to calculate our formula to see if there's an agreement. And remember also that these ones are in the raw figure. 29 plus 15, I think that is 44. And this one too is, okay, they are both 44. So 44, 44, and that makes a total of 88 patients that were seen. Our formula for PO is just agreement between this and that. And our formula for PE, we'll need to find the marginal scores, PA, QA, QA, PB, QB. Now, the first thing to do is we convert this into proportion. We are not using the raw score. We convert them into proportion. So our A here is supposed to be 29 over 88 times 100. Our B is 15 over 88 times 100. Our C is 8 over 88 times 100. D is 36 over 88 times 100, because everything should add up to 100%. We need to calculate that, and then we find the marginal values, for calculating our PE. We need the marginal values. So that is that here. If we convert them to percentages, that is what we have here. Like I've told us how we calculate it. So our PO here is A plus D, that's 0.32 plus 0.409, and that's what gives us 0.738. Then we can calculate our PE following the formula of our marginal scores, of our marginal scores. And if you calculate the formula, you follow it, and then you end up with 0.4991. We can just insert these figures, this one and this one, into our formula. And when we do everything, we have 0.477. And then what does that mean? We go and look at our, what's it called? Our table. It is somewhere here. It's still a moderate agreement. It's not so strong. It's a moderate agreement. And then you interpret it. Now, all this data I've said, it's something that SPSS also calculates, and you can extract your finding and put it in a table. This is a sample table of a Cohen's Kappa. So I said here that the survey instrument was re-administered to 6 randomly selected community pharmacists after a week of filling the first questionnaire to assess the internal reliability of the instrument. And below is the table. That's the Cohen's Kappa showing substantial agreement. Why is it substantial? You can see the value here, 0.646. Let me look at the table. 0.646, you can see it's substantial. Okay, and then we have our confidence interval and we have our p-value. That shows that I'm having an echo.
Oh, sorry. Just to let you know that we are already on top of the hour, so we have 20 minutes more, sir.
The last slide. Or thereabouts. So that's the way the table, that's the way the table looks, and then you can explain your value based on the interpretation. How do we apply it? We do it in a pilot study. We do it when you are training and calibrating research assistants. When you are checking the reliability of your questionnaire, you are checking inter and intra-examiner reliability. Thank you very plenty. And then I have an SPSS, the same data set I have. This time around, I want us to look at, to do simple linear, simple linear regression. Let me just write the question for the linear regression. That is age and lipid. That for the simple linear regression. And then we are going to also look at the multiple linear regression, where we have age, income, and education, and on lipid, okay? And then we are going to look at logistic regression, where I will look at income, the influence of income on hypertension. Remember, my hypertension is binary. It's either present or absence of of hypertension. So I will just quickly stop sharing. I will go to the SPSS, SPSS data set, and we'll quickly see these examples before we are done. So my first example is simple linear regression, and I want to look at the relationship or the effect of age on lipid. So I go to analyze, and from analyze, I go down to regression. As you can see, regression here, and under regression, there are so many regression. I need to know the one I'm choosing. I'm choosing the simple linear. So I pick linear regression. And you can see here, that was why we spent a lot of time talking about dependent variable, independent variable. You must know what a dependent variable is. Okay, so for my dependent variable, I said is the lipid level. So I pick my lipid level, I push it to my dependent variable. And I'm checking the influence of age, baseline age. I put this as my independent variable. Okay, let me check my statistics. Okay, let me just add confidence interval. By the way, I'm not an expert with SPSS. I'm just trying my best, the little I know, and I think it suffices. I've been able to do a bit of work there. So I have that done, and then I go to OK, and I have now opened up my, I have to share the output screen, and we'll continue from that. From that screen. So you can see the regression here, and you can see the model summary, and you can even see our R squared. By now, you know what an R square is. And you can see that it has an ANOVA analysis even before the main finding here. Okay, so I come here. By now, I have told us that the constant here means our intercept. My intercept here is 175.8. And the lipid level here, the age is 1.15. That is my gradient or my coefficient. So if I'm to write maybe like a regression equation here, it will be y equals to 175.8 plus 1.15x. That is my regression equation. And if you look at my p-value here, it is very significant. So that shows that age definitely has an effect on the lipid value. That's just for the simple linear regression. So I go back again for the multiple linear regression. I go to my regression, and then this time around, I will still go to the simple linear because this is where I can add more variables to make it multiple linear. So I have age. I'm going to add income. I add income there. Let me also add educational level. I add educational level. So you can see here now I have 3 independent variables that had automatically made it a multiple linear. I just go on and then I click my OK. So it has shown me the variables that were in there, my educational level, my income, that's in Naira per Naira, and then my baseline age. And here now, you can see that my R squared has improved from the former one that was 0.39. Now I have 0.58. That means that other values have come in to explain my lipid level. Anyway, this is my coefficient. And my constant, like I told us, is my intercept. I have my baseline, that is the coefficient for age, coefficient for Naira, that's my income, coefficient for educational level. And if you look at my p-value, it is only my age that is still significant as a predictor of my lipid level among the 3 different independent variables that I have added. So lastly, let me quickly do a logistic regression where I'll be looking at the influence of income on hypertension. So I go to my analyze, I go to regression, and I regression here, and then I come to binary logistic. I click my binary logistic, and it's asking me for my dependent variable. I'm still working with lipid. I put that as my, no. In logistic regression, our dependent variable is binary. So I said I was working with hypertension. I put my hypertension there, and then I'm looking at the influence of income on hypertension. So I put maybe my Naira here, I put it here. Now, if I just do one independent variable, that's just a simple binary logistic regression. If I add other variables, it makes it multiple binary regression. Okay, and then I continue, and then I have it here. Let's continue. That is hypertension, yes or no. I have my word equation here. The variables that I have here is income, and then many observations. But this is what we are looking for. This is what we are looking for. Variables in the equation. My income is minus 0.003. That is my coefficient. This is my constant. That's the intercept, minus 0.281. Anyway, remember that I said in logistic regression, we are looking at the odds ratio, and that's the exponential B. Both of them are not significant by value of the p-value I'm seeing here, but for my income, you can see that my income is just more like 1.997, it's just like 1. And we have said that in interpreting odds ratio, if it is equal to 1, that means that there's no relationship, there's no effect, there's no association, whatever. So invariably, my income does not have anything to do with hypertension in this particular sample that I have. If you are rich or you are poor, it doesn't have any effect on your hypertension. Can I just quickly check if I can, that same logistic regression. I'm just thinking of something maybe like looking at age, binary logistic. Let me remove my income and let me put my age and see if it has an effect, on hypertension. And I click OK, and then I go down, and you can see, just as expected, my age is very significant, and that's logical. I mean, the older you are, the higher the tendency of ending up with BP. And you can see, although my, my odds ratio is not, is like no association, but age as a variable is a significant predictor of hypertension. Although here in my odds ratio is not really bringing out anything about if it is compared to a particular group or not. But age as a variable is a significant predictor of hypertension. I want to use this opportunity to really thank you very much for your time over these 4 weeks. I hope I've been able to at least add up to a bit of an understanding of quantitative data analysis. I will be ready to attend to our questions. Thank you so much.
Thank you, and thank you very much. Really appreciate you for all you've done for us. We have a couple of questions on the chat, which we will take within the next 10 minutes so that we have time to address some other things. So I will quickly go through them. I think Prof has answered some of them. All right. What is the difference between chi-square and regression analysis, and why the name regression?
Okay, so the name regression. Okay, I'm still having that echo. The name regression is just like, it's a strong tool. It's basically for estimating and predicting. Chi-square does not predict, chi-square does not estimate. Chi-square just gives you the relationship or association between two variables, categorical variables. But regression tells you what can happen. If you have the value of one, you can predict the value of the other. So I think that's the basic thing. And regression is basically has to do with a continuous dependent variable. But chi-square is a non-parametric test, works with categorical variables. Does that make some sense?
Yes, sir. Thank you, sir. So the next one I'm picking here is, how can random forest enhance prediction?
How can what? Random forest?
Random forest. Yes.
Okay, so we are not going to that level, in these last 4 classes before we scatter all of we have built. Maybe that person can private chat me so that we can discuss that. That's an advanced, I think for...
That's an advanced, I think for... Yeah, definitely. Yeah. Yeah. Can I assume the coefficients of determination is the same as size of impact? Oh, okay, Prof, I'll respond. Okay, if you want to take it, sir.
Come again.
Oh, he's asking, can he infer that coefficient of determination is the same thing as size of impact?
Yeah. So we call that effect sizes. So that coefficient of determination just makes us to know the impact of a particular variable or sets of variables on the dependent variable. So it can be taken like that. Yeah, it's a good explanation that you have chosen. Effect size.
Okay. Effect size. Yeah, someone is asking, if I have 0.5, I guess the person is referring to the odd ratio. Can I say it is 0.5 times less likely, or must I inverse it to be able to use less likely?
0.5. Even if you invert it, it's still going to give you the same figure. So because it's just halfway, the mere fact that it's less than 1 makes it less likely or less odds or whatever. So because it's 0.5, it's 0.5, even if you invert it. So that doesn't change anything.
Thank you, sir. So there's a question here. How can we determine sample size from unknown population?
Okay, that one is a separate. If you recollect at the beginning of the class in the research process, sample size calculation is a separate topic. I mean, it's not part of not part of the curriculum for this. Maybe in future, if we have another opportunity, if classes are set up, I'll be able to discuss that. As you might also want to talk with me privately, because it's going to take time to talk about sample size here and now. You don't have all the time.
Absolutely, sir. Thank you. Someone is asking, how do we factor in the mediating variable when analyzing using regression?
Beautiful question. The same way we factor in confounders. So your mediating variable, you will have taken measurements. You have data on them also. So you put them in your multiple regression analysis. You get the point. There is a particular method of analyzing multiple regression. We call it the enter method. Let's assume you have maybe 7 or 8 different variables that you want to put in your, in your regression analysis or your regression model. You can start by putting 2. And then you keep adding them one by one, till you end up with the 8. And you are checking the model to see if it is of good fit using your coefficient of determination. It will get to a time that you put a particular value or a particular variable, and then your coefficient of determination will not change. That shows that that variable has no effect on that model. Even with the model, with the variable, without the variable, it has no effect. And that's how you get to know the influence of variables on your model to see if one is a confounder or another one is a mediator.
Thank you, sir. So someone is asking, Cohen's Kappa, for Cohen's Kappa to work, is the minimum sample size, is there a minimum sample size to use Cohen's Kappa?
Okay. I've not looked at that part. A Cohen's Kappa, there's no Oh, good question. Frankly speaking, I'm not looked at that. But I mean, you have some reasonable number to be able to work with. Because if it is too small, you might not be able to get, for example, if you are working with just like 3 or 4 sample size, it doesn't have any. No, I think you should have something reasonable, but I've not checked. That can be checked out anyway.
Thank you. Okay, someone is asking Cohen's Kappa on SPSS. I don't think we have time to do that. The next question is, kindly differentiate between crude odd ratio and adjusted odd ratio.
You know what I'm saying? In one of the slides, I think I deliberately just hit the slide because it has a bit of explanation. Anyway, in a nutshell, when we say adjusted odds ratio, adjusted is in the sense that it has factored in the other independent variables before giving us that particular figure. The crude odd ratio is just like the particular odds ratio for that particular variable. When we say adjusted, it has factored in, for example, if you have more than 2 or 3 variables. Crude is just the odds ratio for one variable. Adjusted has taken into effect the effect of other independent variables in determining the outcome or the dependent variable. It's now giving a holistic view. Yeah, that's the way you can put it. It's more like this coefficient of determination. When you have for one variable, you have a figure. When you have for 2 or 3 variables, the figure changes. I can say the one that has changed now is the adjusted one, invariably. But for the odds ratio, it's something like that. If you have the crude, is 1 for one variable, the adjusted has taken the effect of other independent variables in the model, in the regression equation. And the person can also like on Google, it will give more information, but that's just the summary of what it means.
Okay, thank you, sir. There's a question here asking that, is Cohen Kappa for reliability? I mean, you said we can use Cohen Kappa for reliability of questionnaire. Can it be compared to Cronbach's alpha test?
Can it be compared to
Cronbach alpha test?
Good. An example of reliability assessment. Cronbach there are different methods you can use.
Okay, sir. Okay, someone is asking, for binary logistic regression, must the independent variable be binary?
It can be any form.
Okay. So I think all we have here is thank you. Oh, someone is asking for sample size determination, but you've mentioned that should be another class. Yeah, a lot of thank you. Okay, I have a question here. What regression model do we use when there are multiple continuous independent variable and multiple ordinal or nominal dependent variable? I think you're okay. Let me just allow you to take it.
That would be multivariate. You'll be having multiple dependent variables at the same time. For a situation like that, you separate your analysis into one dependent variable. In the situation where we have multiple dependent variables, multivariate regression, where the dependent variables are both continuous variables.
Thank you very much. So somebody's saying that in descriptive analysis, how do we know which variable to describe? Does it depend on the research question as well?
The variable is dependent on the type of variable. We spend a lot of time if a variable is categorical, it is ordinal, and the kinds of descriptive statistics that you can use. So your research question definitely will guide you into what to do, because descriptive statistics is just to summarize and to organize your data. That's all it does. You can organize all your data, all your questions, and then you can now go a step further in trying to, analyze to see if they have any relevance for inferential statistics. So your research question will, for example, you are doing a study, you want to know the average age or the average weight or the average height. That's a research question. So when you are describing your data, you will have to do descriptive statistics, maybe mean, median, mode, and standard deviation. for that particular variable. So like you said, your research question will also guide you in the particular variable and the particular method to describe it.
Thank you, sir. As somebody here, I can see birthday cake all over the screen, but I'll come back to that. Someone is telling me, sir?
No, I'm laughing. No, I'm
laughing. All right. So there is somebody here.
Actually.
Yes, that's why I said I'll come back to that. All right. So somebody is appreciating, he says from engineering, but he appreciates he learned a lot from the session. Okay, there is a question here asking what's he learns that regression is about contribution. I don't know if you get the question clearly.
Contribution.
Yes, contribution.
I don't understand.
I don't understand.
About estimation and prediction. That's how I can summarize.
Yeah. Okay, we're just about on. Okay, let me just take this last one. What is the difference between ANOVA and ANCOVA? Yeah, that will be the last question.
ANCOVA is more analysis of covariance, not analysis of variance. How do I describe this? Now it's in ANOVA we are checking the mean, the mean between different groups, but here you are checking the covariance, not necessarily the mean. I deliberately was quiet in many of these. I want us to know that all we have discussed is just like a tip of the iceberg. There's a whole lot of quantitative data analysis, but the ones we work on are the commonest type anyway that you will easily come across. So but ANCOVA is analysis of covariance, and there are specific questions that will require you to use that particular analytical tool instead of the normal ANOVA. Let me just stop there.
All right, thank you very much. There is no better way to celebrate a birthday than imparting knowledge into hundreds and of researchers who will definitely have a ripple effect of passing the message learned to other people. So with that, I'm celebrating you and wishing you a very happy birthday. Let me just share one or two things about Professor Taiwo. He's a head of an institution, he's a very busy man. And to add to it that he actually have to move from his location to somewhere else every Saturday to ensure that he has a good reception to be able to have this session. So he made a lot of sacrifice to ensure that we learn in this person. I can assure you, we appreciate what you've done for us. And I'm sure the audience, as you can see, a lot of birthday wishes and thank you on the chat box, showing how much you appreciate what you've done for us. And we hope that when we call on you, some other time you will be available for us. Thank you very much for the sacrifices you've made.
I appreciate you.
Thank you. This will be the last session. The conversation will continue on the chat box. But you can keep the happy birthday messages coming and all the well wishes. I will now stop recording and I'll give you access to say happy birthday. I think it will be good to sing a happy birthday music to everybody, from everyone. Let me see if I can do that. Just a minute, please. All right. Stop recording the session. I think we can all sing in happy birthday.
Happy birthday to you. Happy birthday to you.
Happy
Happy
birthday
birthday
to you.
to
Happy birthday to you.
May the good Lord bless
In the good Lord, more years
Lord bless you.
the good Lord bless
For he is a good man.
God bless you and increase you. God bless you above.
Thank you all. God bless you all so much.
For he
Appreciate
is a good